In this video, we're going to be examining convergence on a different level. We're going to be talking about a different test, and this test is called the ratio test. So we're going to learn about the ratio test. We're going to learn maybe some math that you haven't learned before in terms of something called a factorial, but let's go ahead and take a look at the definition or the theorem really of the ratio test. And it says, let a sub n be a series with positive terms, and suppose that the limit as n approaches infinity of the next element, okay, or the one more element than the series, a sub n plus 1 divided by a sub n equals some number rho. Now, it's important to note that this is not the sum of the series. You're just taking a ratio of the next element to the previous element, okay? So we know that it's going to either converge or diverge up to the nth element, but the very next element should also either converge or diverge. So it says then the series converges if this ratio rho is less than 1. The series will diverge if rho is greater than 1 or is infinite, okay? Or the test will be inconclusive if rho equals 1. So we're going to take a look here at an example, and it says use the ratio test to determine if the series converges or diverges. Okay, so let's go ahead and take a look and see what we can come up with. Okay, so let's see here, right here. All right, move this, adjust this a little bit. There we go. All right, so let's see. We know we need to find the limit as n approaches infinity of a sub n plus 1 divided by a sub n. So this one may not look very nice preliminarily, but it's actually going to work out to be very nice at the end. So just bear with me here. So let's see what we've got. We're going to have to plug in n plus 1 in for n. So we're going to say 2 to the n plus 1 now, plus 5. All right, divided by 3 to the n plus 1 shall be divided by the original, which was 2 to the n plus 5 divided by 3 to the n. So it looks a little bit funny. And as I always tell my students when dividing fractions, always remember to KFC, that is, keep the first, flip the second, and change the sign from division to multiplication. All right, so let's go ahead and take a look at this right here. What does this look like? Well, this is the limit as n goes to infinity of 2 to the n plus 1 plus 5 divided by 3 to the n plus 1 multiplied by 3 to the n over 2 to the n plus 5. And it looks just like that. So you should kind of start seeing some things that are going on here. Namely, first of all, the 3 to the n you can factor out, you can eliminate. Okay, this is just going to leave you with a 3 to the first power, if you will. Okay, and then you're going to have something that looks a little bit like this. So let's take a look at what it looks like. Limit as n goes to infinity. We have 2 to the n plus 1 plus 5 divided by a 3 that gets multiplied by 2 to the n plus 5. Okay, so what I would tell you to do next, you're talking about a limit at infinity. My students are very familiar with something called Bobo Botno eats DC, and we kind of go through the motions of that. But in this case, we're going to just divide out this big power 2 to the n. Divide out the 2 to the n from every single term. All right, not that 3 in the front, but everything else will. Okay, that 3 is just a scalar multiple. All right, but from every term component, we divide the 2 to the n out. Okay, and we end up seeing what we're left with. Here, we're left with just a 2. Okay, so let's see what that looks like. Let me just rewrite it then. The limit as n goes to infinity, you're left with a 2 plus 5 over 2 to the n divided by a 3 times a 1, because 2 to the n divided by 2 to the n is 1, plus 5 over 2 to the n. All right, now we can approach infinity, because 5 divided by 2 to some infinite power, well, that right there is just going to go to 0. Similarly here, this goes to 0. It's the same thing. And you're left with basically a 2 in the numerator and a 3 times 1 in the denominator. You're left with 2/3. And this right here is your rho value. So what can we say? All right, so I say therefore, rho is less than 1. What does that mean? That means that this converges. All right, and there's really nothing to it. It converges just like that. Okay, so let's go ahead and take a quick pause here because we're going to work on another example, but I've got to introduce a concept first. So let's take a pause. Okay, in order to do the next example, we're going to have to talk about a definition here, and that is factorial notation. So we see an N with an exclamation mark, and it looks kind of funny to have some punctuation in a math class, right? But we actually read it as N factorial, and it is the product of an integer and all the integers below it. So we start off with an example first of a number like 4 factorial. And so 4 factorial is going to be 4 times 3 times 2 times 1, and you can evaluate that. It gives you 24. But if you're talking about n factorial, it's n times n minus 1 times n minus 2 times n minus 3, and so forth and so on until you get to 1. Okay, so that's what n factorial looks like. So it's important for us to go over that definition because we're going to need to apply it now to the ratio test when we're looking at this, because we need to find the n plus 1th element, if you will. So recall how we go about doing that. We look at the limit as n goes to infinity. We're looking at the series a sub n plus 1 to a sub n, okay, the ratio of those two. So this one's going to look a little bit interesting, and I hope you can follow along with me here. But we have basically a 2 times, instead of n plus 1, and we close that off, factorial, divided by n plus 1 factorial times n plus 1 factorial. And you're probably wondering who sits around and comes up with this kind of stuff, right? But at any rate, it is a function or a series in this case that exists, and we analyze it as such. So we take that n plus 1, a sub n plus 1, and we're going to divide it, find the ratio from that to a sub n, which was the original. So we're going to write that out as well. And we have something that looks like this, which is we're just copying and pasting. And again, I always tell my students KFC. All right, keep the first, flip the second, change the sign. All right, so let's see what this looks like. Okay, we have the limit as n goes to infinity. We have, I'm going to distribute that 2. So I'm going to say 2n plus 2 factorial, okay, divided by n plus 1 factorial times n plus 1 factorial multiplied by an n factorial times n factorial divided by 2 to the n factorial. Now we're going to play around with this stuff here, all right, because we're going to use the factorial definition, all right, that I gave you earlier to help eliminate some things, and you're going to see how it's actually going to work out to be really, really nice. Okay, just remember that each successive step of a factorial is one less than the previous. All right, if you can keep that in mind, then it'll make some sense. Okay, so let's rethink the way that it looks, because that's all we have to do is reimagine this. So get creative. So what we're going to do is we're going to say, okay, well, 2n plus 2 factorial is just the product of 2n plus 2, and then I'm going to subtract 1, 2n plus 1, and then I'm going to subtract 1, and then 2n factorial. We can stop there, and you're going to see why in just a second. But let's continue with the n factorial, and we're going to divide again. Now the n plus 1, remember what that means, n plus 1 factorial. Well, that's n plus 1, and then you subtract 1, which is going to give you an n factorial, and you can stop there. And then the same thing happens, n plus 1 times an n factorial, because you subtract 1. We're using the factorial definition against itself, if you will. Okay, so what that does, what that accomplishes for us, is it actually helps eliminate some things. So what you can see here is, oh, and then we also can't forget we had this 2n factorial in the denominator as well. All right, so that eliminates some things. So you should start seeing what's going to get eliminated. First of all, and let me change my color real quick, the n factorials get eliminated. All right, there we go, they're gone. The 2n factorials get eliminated. They're gone as well. All right, we've gotten rid of all the factorials now. So let's go ahead and rethink the way that this looks one more time. This is the limit as n approaches infinity. And I see that I have 2n plus 2, but watch this. The greatest common factor is 2, so I'm going to factor out 2. 2 times n plus 1 times 2n plus 1 divided by n plus 1 times n plus 1. Okay, and I can eliminate an n plus 1 factor. There we go. I can then distribute my 2. All right. So what do I end up with? The limit as n goes to infinity, I have not 2, but rather 4n plus 2 divided by n plus 1. And I can divide out my n now. I can divide everything by n. All right, everything by n. All right, and I can rethink my limit now. So what does this limit look like now? All right. The limit as n goes to infinity of basically 4 plus 2 over n divided by 1 plus 1 over n. And now we can say n approaches infinity. This goes to 0. This goes to 0. What am I left with? I am left with something that equals 4. So this is my rho value. Well, what do I know about rho? And let me rewrite that. Rho being greater than 1. Okay, it's 4 in this case. So rho being greater than 1 means that this one right here, in fact, diverges. All right, so it diverges. And that's our answer here for this one right here. Because we go back to, again, the definition up here at the top that said if rho is less than 1, it converges. If it's greater than 1 or is infinite, it diverges. And if it equals 1, it's inconclusive. But this hopefully helps and makes some sense here when we look at the definition and the grand scheme of things. Okay, so as always, I hope this video was helpful. And remember, like and subscribe.